Hello, friends. Welcome back to another quiet journey through the cosmos. Some nights the universe whispers in code. In 1967, a young graduate student named Jocelyn Bell sat alone in a cold radio observatory, scanning miles of paper charts that tracked the invisible sky. Most nights brought only static, the random crackle of distant stars and galaxies breathing their ancient light across the void. But on one particular evening, something different emerged from the noise. A pulse, regular, precise, repeating every 1.337 seconds, with a rhythm so exact it seemed almost intentional. Too steady to be natural, too perfect to be real. For a brief, wild moment, the team wondered if they had found something extraordinary, a signal, a message, a hello from across the stars. They even gave it a name, half joking, half hopeful, LGM1, Little Green Men Number 1. Before we drift into this story, if you find peace in these quiet explorations of the universe, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Tonight, we follow the pulse. We'll trace the story of how dead stars became the universe's most faithful lighthouses, how their steady rhythm helped us map space itself, and how in their relentless spinning, they revealed secrets about the nature of matter, time, and the strange beauty that emerges from endings. You don't need to understand everything. Just rest and let curiosity do the listening. The signal Jocelyn Bell discovered wasn't from little green men, of course. It was something far stranger, far more beautiful in its own way. It was light from a star that had died, but refused to go quietly into the dark. What she had found was the first pulsar, a cosmic lighthouse spinning in the void, sweeping its beam across Earth with the precision of a metronome. Scientists would later name it PSRB 1919 plus 21, a string of numbers and letters that could never quite capture the wonder of what it represented. Proof that even in death, stars find ways to sing. Pulsars are neutron stars, the collapsed cores of massive suns that once burned hundreds of times brighter than our own. When such a star exhausts its fuel, it can no longer hold itself up against its own crushing gravity. The outer layers explode outward in a supernova, a blast so violent it can briefly outshine an entire galaxy. But the core, the heart of the star, collapses inward. Electrons are forced into protons, creating neutrons, and what remains is a sphere perhaps 20 kilometers across, but containing more mass than our entire sun. Imagine all the light, all the fire, all the fury of a star compressed into something roughly the size of a city. The numbers alone seem impossible. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth, more than all the cars, buildings, and people in a large country, condensed into something you could hold in your palm if your palm could somehow survive. The surface gravity is so intense that if you could stand on a neutron star, which you absolutely could not, you would be flattened to a layer about an atom thick in a fraction of a second. Light itself struggles to escape bent and twisted by the overwhelming gravitational field. But what makes a neutron star become a pulsar is not just its incredible density, it's the spin. When the core of a massive star collapses, something remarkable happens. The star was already rotating slowly, as all stars do, turning leisurely over days or weeks. But as it shrinks, the laws of physics demand that it must spin faster to conserve angular momentum, the same principle that makes an ice skater spin faster when she pulls her arms in close. A collapsing star pulls its arms in dramatically. What once turned slowly across millions of kilometers now spins violently across mere tens of kilometers. The rotation accelerates to impossible speeds, sometimes hundreds of times per second. And with that spin comes something even more extreme: magnetic fields. The magnetic field that existed in the original star gets compressed along with everything else, but magnetic field strength increases with the square of the compression. A star that shrinks by a factor of 100,000 sees its magnetic field increase by 10 billion times. The result is the strongest magnetic field in the known universe, 1 trillion times more powerful than the strongest magnets we can create on Earth. 1,000,000 trillion times stronger than Earth's own magnetic field. These fields are so intense they would be lethal from thousands of kilometers away, ripping the iron from your blood before you could even comprehend what was happening. It's this combination, the furious spin and the crushing magnetic field, that creates the lighthouse effect. The magnetic poles of a neutron star don't align with its rotation axis, just as Earth's magnetic north doesn't sit exactly at the geographic North Pole. Charged particles spiral along the magnetic field lines, and as they accelerate near the magnetic poles, they emit radiation, powerful beams of radio waves, X-rays, sometimes gamma rays. These beams shoot out from the magnetic poles like light from a lighthouse. And as the neutron star spins, those beams sweep through space. If Earth happens to lie in the path of that sweeping beam, we see a pulse, flash, dark, flash, dark, a cosmic heartbeat. The first pulsar Jocelyn Bell discovered pulsed roughly once per second. But as astronomers turned their radio telescopes toward the sky with new purpose, they began finding others. Some pulsed every few seconds. Others astonishingly pulsed many times per second, each one a neutron star spinning in the dark, broadcasting its existence to anyone willing to listen. Within a few years, dozens were known. Today we've cataloged over 3,000. What strikes me most about pulsars is their constancy. In a universe defined by change, by stars being born and dying, by galaxies colliding, and black holes consuming everything nearby, pulsars are almost absurdly regular. Their pulses arrive with a precision that rivals and sometimes exceeds our best atomic clocks. Astronomers can predict when the next pulse will arrive down to microseconds, sometimes nanoseconds. This is a dead star, mind you, a remnant, a ghost. And yet it keeps time with a faithfulness that puts the living universe to shame. There's a lesson somewhere in that steadiness, perhaps. That even after catastrophic endings, after everything falls apart, there can still be rhythm, still be order, still be something to hold on to in the vastness. But the story of that first discovery of Jocelyn Bell, sitting with her charts in 1967, carries its own quiet tragedy. She was a graduate student working under her advisor, Anthony Hewish, when the Nobel Prize in Physics was awarded in 1974 for the discovery of pulsars. It went to Hewish and another astronomer, Martin Ryle, for their work in radio astronomy. Jocelyn Bell was not included. The young woman who had actually noticed the strange signal, who had insisted it was real when others dismissed it as interference, who had painstakingly traced it across the sky, received no credit from the Nobel Committee. She has spoken about this with remarkable grace over the years, noting that Nobel Prizes rarely go to graduate students. But the scientific community remembers. Her name is inseparable from pulsars. History, if not the prize, belongs to her. It makes you wonder how many other signals we've dismissed. How many other students looking at data everyone else thought was noise saw something real, but were never believed? How much of discovery is simply the courage to say, this is strange, and strange might mean something. The name pulsar itself is almost playful, a contraction of pulsating star. Though technically they don't pulsate at all, they simply spin, and we see the result as pulses. But the name stuck because it captured something essential about the experience of detecting them. That steady, insistent beat, like a heart, like a drum, like something alive even though the star itself has long since died. And that's the beautiful contradiction at the center of pulsars. They are endings that refuse to end, deaths that still shine, silence that somehow still speaks. In their last act before fading into cold, dark, invisible spheres, drifting through the void, They become the universe's most reliable timekeepers, the brightest beacons, the steadiest voices. They are proof that even collapse can create something extraordinary. When Jocelyn Bell first saw that repeating signal, she didn't immediately think of collapsed stars and extreme physics. She thought briefly about life elsewhere, about intelligence, about the possibility that someone out there was trying to reach us. In a way, the truth she discovered was almost as profound. Not intelligence, but physics at its most extreme. Not a message, but a consequence of nature pushed to its absolute limits. The universe doesn't need to be populated with other minds to be full of wonder. Sometimes the laws of physics alone, playing out across cosmic scales, create something that feels almost intentional. The pulsar keeps spinning, the beam keeps sweeping, and we, tiny and brief on our small blue world, listen to the pulse and understand just a little that the universe is stranger and more beautiful than we ever imagined. In the next part of our journey, we'll step closer to the moment of creation, to the supernova itself, and watch as a star tears itself apart to birth something utterly unlike anything else in the cosmos. We'll see how collapse becomes compression, how gravity defeats even the atoms themselves, and how what emerges is not an ending, but a transformation into something almost unimaginable. Stars don't die quietly. For millions, sometimes billions of years, a massive star burns steadily, fusing hydrogen into helium, helium into carbon, into heavier elements, each fusion reaction releasing energy that holds the star up against its own weight. But fusion has limits. Eventually, the star runs out of fuel it can burn. Iron accumulates in the core, and iron, unlike lighter elements, takes more energy to fuse than it releases. The fire goes out. And when the fire goes out, there's nothing left to hold the star up. Gravity wins. In less than a second, the core collapses. What happens next is one of the most violent events in the universe. The collapse is almost incomprehensibly fast. The core, which might have been roughly the size of Earth, shrinks to a sphere about 20 kilometers across in a fraction of a second. Imagine crushing our entire planet, all its mountains and oceans and molten iron core down to the size of a city. The outer layers of the star, suddenly unsupported, fall inward at nearly a quarter of the speed of light. When they hit the rigid neutron core that is formed at the center, they rebound. The shockwave blasts outward, tearing the star apart in a supernova explosion that can briefly outshine every other star in the galaxy combined. For a few weeks, a single dying star can be visible across millions of light years, a cosmic scream announcing its own ending. But let's stay with the core, because that's where the real strangeness happens. In the crush of collapse, the very structure of matter breaks down. Atoms are not mostly empty space anymore. Under normal circumstances, electrons orbit far from the nucleus, and the distances between them are vast on atomic scales. But when gravity becomes strong enough, those distances disappear. Electrons are forced into the nucleus itself. They combine with protons to form neutrons, and what's left is a ball of neutrons packed so tightly that the entire star has roughly the density of an atomic nucleus. It's matter in a state that simply doesn't exist anywhere else in the universe except in the cores of neutron stars and perhaps inside black holes. The numbers are difficult to hold in your mind. A neutron star with a mass of about 1.4 suns, squeezed into a sphere 20 kilometers in diameter. Density around 400 trillion times that of water. A single teaspoon, about 5 milliliters, would weigh somewhere between 500 million and 1 billion tons, depending on exactly where in the star you scooped it from. That's more than the combined weight of all humans currently alive, condensed into something that could fit in a spoon. If you could somehow bring a piece of neutron star material to Earth, it would punch straight through the planet, like it wasn't even there, falling toward the center under its own impossible weight. The surface of a neutron star is thought to be a rigid crust made mostly of iron nuclei, arranged in a crystalline lattice, but under pressures and densities that make it incredibly strong. Some scientists suggest this crust might be the strongest material in the universe, billions of times stronger than steel. Beneath the crust, things become stranger still. Neutron-rich nuclei exist in bizarre shapes, sometimes called nuclear pasta, because the arrangements resemble spaghetti lasagna and other pasta shapes, though made of nuclear matter rather than wheat. Deeper still, there may be a core of superfluid neutrons, a quantum liquid that flows without any friction whatsoever, perhaps mixed with exotic particles that we can only theorize about. We've never been able to recreate these conditions in any laboratory. The centers of neutron stars remain in many ways as mysterious as the interiors of black holes. And then there's the spin. This is where conservation of angular momentum performs one of its most spectacular demonstrations. The original star before collapse was rotating. Most stars do slowly, turning over periods of days or weeks as they burn. Our sun, for instance, rotates once roughly every 25 days at its equator. A massive star might turn even more slowly given its size. But when that star collapses, its rotation rate must increase to conserve angular momentum. It's the ice skater pulling in her arms, but taken to an almost absurd extreme. A star that was perhaps 1,000,000 kilometers across, turning leisurely, becomes a star 20 kilometers across. The rotation speeds up by a factor that can reach hundreds of thousands, even millions. Suddenly, what was rotating once every few weeks is now rotating tens, hundreds, even over 1,000 times per second. The fastest spinning pulsar we've ever discovered, PSRJ 1748-2446 AD, rotates 716 times every single second. Think about that for a moment. A ball of matter more massive than the sun, spinning more than 700 complete rotations. In the time it takes you to say, 1 Mississippi, the surface of that neutron star is moving at roughly 24% of the speed of light. Any faster, and the star would tear itself apart, flung outward by its own centrifugal force. It sits right at the edge of what physics allows. But perhaps the most extreme thing created in this collapse isn't the density or the spin. It's the magnetic field. Magnetic fields in stars like angular momentum get compressed during collapse. But magnetic field strength doesn't just scale with size. It scales with the square of the compression. When a star, 1,000,000 kilometers wide, becomes a star 20 kilometers wide, the magnetic field doesn't just increase by a factor of 50,000. It increases by a factor of 2.5 billion. And if the original star had a strong magnetic field to begin with, the result can be almost beyond comprehension. The typical pulsar has a magnetic field around 1 trillion times stronger than Earth's. That's 1 trillion. 1 trillion. Strong enough that if you were somehow standing 1,000 kilometers away, the magnetic field would start to interfere with the electron bonds in your atoms. You wouldn't just die, you would cease to be chemistry. On July 4th, 1054, AD, astronomers in China, Japan, and the Arab world recorded the appearance of a guest star in the constellation Taurus. It was so bright it could be seen during the day for 23 days. At night, it was bright enough to read by. It remained visible to the naked eye for nearly 2 years before fading. What they were watching was a supernova, a massive star ending its life in spectacular fashion, roughly 6,500 light years away from Earth. Today we can see the remnant of that explosion. We call it the Crab Nebula, a cloud of gas and dust, still expanding outward from the blast. And at the very center of that cloud sits the Crab Pulsar, a neutron star spinning 30 times per second, the crushed heart of the star that exploded almost 1,000 years ago. The Crab Pulsar is one of the youngest pulsars we know of, and it's still energetic, still slowing down noticeably as it pours energy into the surrounding nebula. Every day it rotates a tiny bit slower than the day before, losing rotational energy that lights up the gas around it, creating a wind of particles that glow in X-rays and visible light. In a few tens of thousands of years, it will have slowed enough that it might stop producing visible pulses altogether. becoming what astronomers call a dead pulsar. Still there, still a neutron star, but no longer bright enough for us to see. But for now, it spins a cosmic monument to an event witnessed by people who had no idea what they were really seeing, who could only describe it as a new star appearing where none had been before. It's humbling in a way to realize that the light from that explosion, traveling at 300,000 kilometers per second, took 6,500 years to reach Earth. The star actually exploded around 5,450 BC, when humans were just beginning to develop agriculture, just starting to settle in permanent villages. The light traveled through space for millennia, passing through the dark until finally in 1054 it arrived. The people who saw it had no concept of light years, of supernovae, of neutron stars. They saw a wonder and recorded it as best they could. And now, nearly 1,000 years later, we point our telescopes at the same spot in the sky and see not just the light, but the mechanism behind it, the physics, the story of how stars die and what they leave behind. There's a common misconception that all massive stars become neutron stars when they die. They don't. Whether a dying star becomes a neutron star or collapses further into a black hole depends on its mass. If the core left behind after the supernova is less than about 2 to 3 solar masses, it can stabilize as a neutron star. The neutron degeneracy pressure, a quantum mechanical effect where neutrons refuse to be squeezed into the same space, is enough to hold the star up against gravity. But if the core is more massive than that, even neutron degeneracy pressure isn't enough. Gravity wins completely. The core continues collapsing past neutrons, past anything we understand, until it becomes a black hole. The universe has a threshold. Below it, you get a neutron star. Above it, you get a singularity. And we still don't fully understand what determines which path a particular star will take. What we do understand is that in the moment of collapse, a star undergoes a transformation so total that almost nothing of its original structure remains. The atoms that made up the star, forged over millions of years of fusion, are crushed out of existence. The light that once shone from its surface is replaced by something stranger beams of radiation, shooting from magnetic poles powered not by fusion, but by rotation and magnetism. The slow, steady burn becomes a frantic spin. The star that once lived now haunts the cosmos, a ghost made of matter pressed to its absolute limit. And yet, in that haunting, there is light. The pulsar shines. It spins. It broadcasts its existence across the galaxy, a beacon born from catastrophe. Death in the cosmos is never quite the end. It's a transition, a collapse that creates, a silence that still speaks. Soon we'll explore exactly how that light escapes, how the lighthouse beam forms, and why we see it as pulses. We'll look at the geometry of spin and magnetism, at the particles spiraling along field lines, and at the strange architecture that turns a spinning neutron star into one of the brightest objects in the radio sky. Imagine standing on a rocky shore at night, watching a lighthouse sweep its beam across the dark water. The light itself never stops shining, but from where you stand, you see only flashes. Bright, dark, bright, dark. The rhythm is created not by the light turning on and off, but by geometry, by the rotation of the beam past your line of sight. This is in essence how pulsars work. The light never stops. We simply stand in the path of something turning. But the mechanism that creates a pulsar's beam is far stranger than any lighthouse humanity has ever built. It involves magnetic fields strong enough to warp space particles, accelerated to nearly the speed of light, and a geometry that seems almost designed to broadcast across the cosmos. Understanding how a spinning neutron star becomes a beacon requires us to look at one of the universe's most elegant collaborations between rotation magnetism and radiation. A neutron star, as we've seen, spins rapidly and possesses an extraordinarily powerful magnetic field. But here's something crucial that makes the pulsar effect possible. The magnetic axis and the rotation axis don't align. Think of Earth for a moment. Our planet spins around an axis that runs roughly from the North Pole to the South Pole. But our magnetic field, the one that makes compasses point north, doesn't quite line up with that rotation axis. Magnetic north is currently about 500 kilometers away from true north, wandering slowly through the Canadian Arctic. This misalignment is common in rotating bodies with magnetic fields. For neutron stars, this misalignment is everything. The magnetic field of a neutron star extends far beyond the surface, creating what physicists call a magnetosphere, a region where the magnetic field dominates and controls the motion of any charged particles nearby. Near the magnetic poles, the field lines curve and concentrate, creating regions of intense magnetic strength. Charged particles, mostly electrons and positrons, get trapped by these field lines and spiral along them toward the poles, accelerating as they go. And when charged particles accelerate, they emit radiation. This is a fundamental principle of electromagnetism, discovered by James Clerk Maxwell in the 1860s, long before anyone imagined neutron stars. Accelerating charges radiate. The faster they accelerate, the more energy they release. Near the magnetic poles of a pulsar, particles are accelerating, ferociously spiraling along field lines at velocities approaching the speed of light. The radiation they emit is beamed along the magnetic axis, shooting out from the poles in narrow cones of radio waves, X-rays, sometimes even gamma rays. These are the lighthouse beams. They shine constantly, pouring energy into space, but they shine in specific directions along the magnetic axis. And because the magnetic axis is tilted relative to the rotation axis as the neutron star spins, those beams sweep through space like spotlights. If Earth happens to lie in the path of that sweeping beam, we detect a pulse of radiation every time the beam crosses our line of sight. If we're not in the path, we never see the pulsar at all, even though it's there spinning and radiating just the same. This means that for every pulsar we detect, there are likely many more we simply can't see because their beams don't point toward us at any point in their rotation. We're only seeing the ones whose geometry happens to include Earth in the sweep. The angle of the tilt matters enormously. If the magnetic axis is nearly aligned with the rotation axis, the beam sweeps out a small circle in space, and the chances of it crossing Earth are low. If the tilt is large, closer to 90 degrees, the beam sweeps out a much wider path, like a lighthouse, with a beam that rotates horizontally rather than at a slight angle. Some pulsars have such specific geometries that we see 2 pulses per rotation, one from each magnetic pole as it sweeps past. These are called double pulsars. In some contexts, though, that term also applies to binary systems, where both objects are pulsars, which is a different phenomenon we'll explore later. The geometry of each pulsar is unique, and part of the work of pulsar astronomy is figuring out, from the shape and timing of the pulses we receive, what angle the star must be tilted at, how fast it's really spinning, and where those magnetic poles are pointing. The radiation itself comes in different forms, depending on the energy of the particles and the strength of the magnetic field. Most pulsars were first discovered through their radio emission, which is why early pulsar hunters used radio telescopes. Radio waves are relatively easy to detect across long distances, and they pass through the dust and gas of our galaxy without being absorbed. But many pulsars also emit X-rays, which require space-based telescopes to observe since Earth's atmosphere blocks them. Some emit visible light. A few, like the Crab pulsar, emit gamma rays, the highest energy form of light, created when particles are accelerated to the most extreme velocities imaginable. The Crab pulsar is one of the few pulsars we can actually see blinking in visible light, flashing 30 times per second, a strobe in the darkness that you could, in theory, watch through a large enough telescope, if your eye could process flickers that fast. There's a region around the pulsar called the light cylinder, an imaginary surface where if the pulsar were spinning any faster, the outer edge of the magnetosphere would be moving at the speed of light. Nothing can move faster than light, so this cylinder represents a kind of boundary. Beyond it, the magnetic field lines can no longer stay closed and connected to the star. They open up, and particles can escape along them into interstellar space, creating what's called a pulsar wind. This wind carries away energy and angular momentum, which is why pulsars slow down over time. They're not slowing because of friction or drag in any traditional sense. They're slowing because they're flinging matter and energy outward into space, losing rotational energy in the process. The Crab pulsar, young and energetic, loses about 5% of its rotational energy every 1,000 years. That might not sound like much, but given how much rotational energy a neutron star contains, it's enormous. The energy pouring out of the Crab pulsar powers the entire nebula around it, making the gas glow, creating shock waves and particle streams that we can observe across multiple wavelengths. Older pulsars, having spun down over millions of years, release far less energy and eventually become too faint for us to detect, though they're still out there, still spinning, just too quiet for our instruments to hear. Here's something that puzzled scientists for years. How exactly do the particles get accelerated in the first place? The magnetic field provides structure, but magnetic fields alone don't accelerate particles. You need an electric field for that. It turns out that the rotation of the neutron star combined with its magnetic field creates enormous electric fields near the poles through a process called unipolar induction. The spinning magnetic field essentially acts like a giant dynamo, generating voltages that can reach trillions of volts. Particles caught in these electric fields are accelerated to incredible speeds, and as they spiral along the magnetic field lines, they radiate. The details of this process, especially close to the neutron star surface where densities and field strengths are extreme, are still being worked out. Some of the physics happens in regimes we can't replicate in laboratories, so we rely on observations and theoretical models that try to match what we see. One of the beautiful things about pulsars is that they're self-announcing. Unlike black holes, which we can only detect through their gravitational effects on nearby matter, or dark matter, which we infer from galactic rotation, curves, pulsars broadcast their presence. They send out signals that say, "I'm here, I'm spinning, I exist." It's almost generous in a way. The universe could have made neutron stars silent and invisible once they stopped fusing. Instead, they shine, they pulse, they make themselves known. But there's a haunting quality to it as well. The light we see is not the light of life, a fusion of a star burning fuel. It's the light of dissipation of energy slowly draining away. Every photon a pulsar emits represents a tiny loss of rotational energy. Every pulse brings it fractionally closer to silence. Pulsars are in a very real sense running down. They're cosmic clocks winding towards stillness. Young pulsars blaze brightly and slow quickly. Old pulsars whisper and slow imperceptibly. All of them are moving in the same direction, toward quiet, toward dark, toward becoming cold, inert spheres of neutronium drifting through space, invisible and still. And yet, before they fall silent, they give us so much. The regularity of their pulses allows us to test fundamental physics, to measure distances across the galaxy, to detect gravitational waves by watching for tiny deviations in pulse arrival times. Pulsars have become tools, instruments, cosmic laboratories. We've learned more about the behavior of matter under extreme conditions from studying pulsars than from almost any other source. They've taught us about general relativity, about quantum chromodynamics, about the interiors of atomic nuclei. A dead star spinning in the dark has become one of the most scientifically valuable objects in the universe. There's a kind of poetry in that. The lighthouse doesn't need a keeper. It spins on its own, powered by its own momentum, shining not for ships, but simply because that's what physics demands it do. And we distant observers on a small planet have learned to read its light, to decode its rhythm, to understand just a little what it means to be a star that has died but not disappeared, that has ended but not finished. From this understanding of how the beam forms and sweeps, we'll turn our attention to the pulsars that spin fastest. The millisecond pulsars, stars that have somehow been spun back up to dizzying speeds after slowing down, recycled by the universe into something even stranger than they were before. There's a pulsar in the constellation of Sagittarius that spins 716 times every single second. 716 complete rotations in less time than it takes to blink. Its designation is PSRJ, 1748-2446 AD, a string of numbers that tells astronomers exactly where to point their telescopes, but says nothing about the sheer absurdity of what's happening there. This is the fastest spinning neutron star we've ever found, a sphere roughly 20 kilometers across, more massive than the Sun, rotating so quickly that its equator is moving at nearly a quarter of the speed of light. Any faster, and the star would simply tear itself apart, flung outward by its own centrifugal force. It sits right at the edge of what physics allows. How does something so massive spin so fast? And perhaps more puzzling, why would it? We've established that pulsars slow down over time, losing energy as they radiate into space. Young pulsars might spin tens of times per second when they're first born, but over millions of years, they gradually wind down their rotation, becoming slower and slower until they fall silent. So, when astronomers discovered pulsars spinning hundreds of times per second, far faster than any young pulsar, should it created a mystery. These objects shouldn't exist. Something had spun them back up. The answer scientists eventually realized is theft. Or perhaps recycling, if you prefer a gentler word. These millisecond pulsars, as they were called, are old neutron stars that have been given a second life, spun back up to incredible speeds by stealing matter and angular momentum from a companion star. They are, in a very literal sense, vampires feeding on another star to regain something they had lost. Here's how it happens. Many stars form in binary systems, two stars orbiting a common center of mass. If one of those stars is massive enough, it will eventually go supernova and leave behind a neutron star, the companion star. If it survives, the explosion remains in orbit around the neutron star. For a while, nothing particularly dramatic happens. The neutron star spins down gradually, the companion star lives its life, and the system is relatively stable. But if that companion star is close enough, and if it eventually evolves into a red giant, expanding as stars do when they age, its outer layers can reach toward the neutron star. And when matter from one star gets close enough to the intense gravity of a neutron star, it doesn't fall straight down. It spirals inward, forming what's called an accretion disk, a swirling disk of gas orbiting the neutron star at incredible speeds, heating up through friction until it glows in X-rays. As this matter spirals inward and eventually crashes onto the neutron star's surface, it doesn't just add mass, it adds angular momentum. The matter is orbiting rapidly when it hits, and when it merges with the neutron star, that orbital motion gets transferred into rotational motion. Slowly, over millions of years, the neutron star begins spinning faster. The process is called spin-up, or recycling. The old pulsar, which had slowed to perhaps one rotation every few seconds, gradually accelerates. 10 rotations per second, 50, 100, some reach several hundred rotations per second. They are being wound back up like a cosmic spring. The fastest spinning to pulsar P SRJ 1748-2446 AD likely underwent exactly this process. It's part of a globular cluster called Terzan 5, a dense ball of ancient stars, where interactions between stars are common. At some point in its past, perhaps a billion years ago, it captured a companion, or was already in a binary system, and that companion fed it matter for millions of years, spinning it faster and faster until it reached the breakneck speed we observe today. The companion is likely long gone now, either consumed entirely or flung away by the gravitational interactions common in such crowded stellar environments. But the spin remains a gift that keeps the pulsar bright and detectable long after it should have faded. Not all recycled pulsars are alone, though. Some still have their companion stars, and the dynamics of these systems can be extraordinarily complex. In some cases, the neutron star accretes matter gently and steadily spinning up gradually. In others, the process is more violent with bursts of accretion that cause X-ray outbursts we can detect across the galaxy. These are called low-mass X-ray binary systems, where a neutron star is actively pulling matter from a companion star that's less massive than the Sun. We can watch the process of recycling in action, see the neutron star gradually speeding up over decades of observation. And then there are the black widows. The name comes from the spider species, where the female sometimes consumes the male after mating, which is a rather grim metaphor but apt for what's happening in these systems. A black widow pulsar is a millisecond pulsar with a companion star that's being destroyed. The intense radiation and particle wind from the rapidly spinning pulsar is so strong that it's evaporating the companion, stripping away its outer layers bit by bit. The companion is usually a small star, perhaps 1/10 the mass of the Sun or less, and it's slowly being consumed by the very object it helped to create. Over time, millions of years from now, the companion will be completely destroyed, evaporated into space, and the pulsar will be left alone, spinning rapidly with no remaining evidence of where it got its speed. The first black widow pulsar discovered was PSRB 1957 plus 20 found in 1988. Its companion is a brown dwarf, a failed star, barely massive enough to be called a star at all, and it's being steadily destroyed. Astronomers can actually see the evidence in the light curve. When the companion passes in front of the pulsar from our perspective, the radio signal gets blocked. But when the companion passes behind the pulsar's radiation, heats up the side, facing it, causing that hemisphere to glow in visible light. The companion is literally being cooked by the pulsar, its surface temperature varying by thousands of degrees, depending on which side is facing the neutron star. It's a slow execution, a death sentence that will take tens of millions of years to complete. There's a variation on this theme called redback pulsars, named after another spider species. In redback systems, the companion star is slightly more massive, typically between 1/10 and half the mass of the Sun, and it's not being completely evaporated yet, but the pulsar is still stripping material away. These systems seem to be in an intermediate stage somewhere between active accretion, where matter is still flowing onto the neutron star, and the black widow phase, where the companion is being destroyed. Some redbacks switch back and forth between states, sometimes showing X-ray emission from accretion and sometimes showing pulsar behavior. It's a transitional phase in the life cycle of these systems. One of the most remarkable things about millisecond pulsars is their stability. They are, without exaggeration, the most precise clocks in the universe. Some millisecond pulsars keep time more accurately than the best atomic clocks we've built on Earth. PSRJ 0437-4715, for instance, has a period of 757 milliseconds, and astronomers can predict when the next pulse will arrive, with an uncertainty of less than a microsecond, even over time scales of years. This extraordinary precision makes millisecond pulsars incredibly useful for testing physics in ways that would be impossible otherwise. But here's something that puzzled astronomers for years. If you're spinning up a neutron star by dumping matter onto it, adding mass, shouldn't the star eventually become too massive and collapse into a black hole? Neutron stars can only exist up to about 2 to 3 solar masses. The exact limit depends on the equation of state of neutron matter, which we're still working out. Above that, mass gravity wins, and the neutron star should collapse. Yet we see millisecond pulsars that have likely accreted significant amounts of matter, and they're still neutron stars. What's happening? The answer seems to be that while matter is falling onto the neutron star is also losing mass in other ways. The intense radiation pressure from the accretion process can blow away some of the infalling matter before it reaches the surface. The pulsar wind, once the accretion stops and the pulsar turns back on, carries away mass and energy. And in some cases, the companion star might be completely evaporated with much of its mass never actually accreting onto the neutron star, but instead being blown away into space. The balance is delicate. The neutron star gains angular momentum more easily than it gains mass, which is exactly what you'd want if you're trying to spin something up without making it too heavy. Nature seems to have found a way to recycle pulsars without pushing them over the edge into black hole territory, at least most of the time. There's also an interesting observational fact. Millisecond pulsars are relatively rare. Out of the roughly 3,000 pulsars we know of, only a few hundred are millisecond pulsars. This makes sense when you consider what's required to create one. You need a binary system. You need one star to go supernova and leave a neutron star. You need the binary to survive that explosion, which is not guaranteed since supernovae can be asymmetric and impart a kick to the neutron star, potentially breaking the binary apart. You need the companion to evolve and expand at the right time, close enough for mass transfer, but not so close that it merges catastrophically. You need the accretion process to last long enough to spin the pulsar up significantly. And ideally, you need this to happen in a location and orientation where we can actually detect the pulsar once it's been recycled. It's a narrow path, and most binary systems don't walk it successfully, yet the ones that do are spectacular. They're lighthouses that have been rekindled stars that died slowed down, and then came roaring back to life faster than they were before. They're proof that even in the cosmos, endings are rarely absolute. Sometimes, given the right circumstances, even a dead star can find new energy, new purpose, new spin. It doesn't make them alive, of course, but it does make them remarkable, and it reminds us that the universe is full of second acts of renewals born from unlikely encounters of old things made fast and bright again through processes we're only beginning to fully understand. What these millisecond pulsars offer us beyond their scientific value is a kind of lesson in constancy. They've been through so much born in violence slowed by time, spun back up by theft or symbiosis, and yet they emerge from all of it spinning with a regularity that puts every human-made clock to shame. Perhaps that steadiness, that refusal to wobble or drift, is the most striking thing about them. In a universe of chaos and change, here are objects that once set spinning keep perfect time for millions of years. But even perfect clocks can hiccup. Even the most stable pulsars occasionally experience something sudden and strange moments when their steady rhythm breaks, when the spin changes unexpectedly. These events, called glitches, reveal that beneath the surface of even the most reliable pulsars, there's turbulence, there's structure, there's physics we're still trying to understand. On Christmas Day in 1988, astronomers monitoring the Vela pulsar noticed something impossible. The pulsar, which had been spinning with metronomic precision for years, suddenly sped up. In a fraction of a second, it rotated faster than it had moments before, as if someone had reached into space and given it a push. The change was tiny, about 10 parts per million, but for an object that had been slowing down steadily for thousands of years, any increase in speed was shocking. The pulsar had glitched, and in that glitch it revealed that neutron stars are not the simple solid spheres we once imagined. Pulsars are the universe's most reliable clocks. Their rotation is so stable, so regular, that astronomers can predict the arrival of pulses years in advance with extraordinary precision. For some millisecond pulsars, the timing is accurate to within nanoseconds, billionths of a second even over spans of decades. These objects rival and in some cases exceed the precision of atomic clocks built in laboratories on Earth. Atomic clocks, which measure time using the vibrations of atoms like cesium or rubidium, are accurate to about 1 second in 30 million years. The best pulsar clocks match or beat that measuring time using the rotation of an object more massive than the sun, spinning in the vacuum of space 6,000 light-years away. This precision has made pulsars invaluable for testing fundamental physics. When Einstein proposed his theory of general relativity in 1915, he predicted that massive accelerating objects should create ripples in space-time gravitational waves that propagate outward at the speed of light. But gravitational waves are extraordinarily weak, far too faint to detect, with any technology available in Einstein's lifetime. For decades, they remained purely theoretical. Then, pulsars gave us a way to test the prediction indirectly. By timing the pulses from pulsars and binary systems, astronomers could measure whether the orbit was changing in exactly the way general relativity predicted it should, if gravitational waves were carrying energy away. We'll return to that story soon. For now, the point is simpler. Pulsars keep time so well that we can use them to measure effects that would be invisible with any other instrument. But pulsars are not perfect clocks. They slow down gradually, losing rotational energy as they radiate and as particles stream away in their pulsar winds. This slowdown is smooth and predictable, typically measured in nanoseconds per day. A young pulsar like the crab might slow by about 38 nanoseconds every single day, a tiny but steady decrease that accumulates over years. Older pulsars slow down much more gradually, but they still slow. The universe, it seems, wants spinning things to stop. Except, sometimes they don't. Sometimes a pulsar suddenly speeds up. These events, called glitches, are abrupt changes in the rotation. Rate increases in spin that happen over seconds or minutes, and then gradually decay back toward the long-term slowdown trend. Glitches are not rare. The Vela pulsar glitches roughly once every 3 years. The Crab pulsar glitches less frequently, but when it does, the change can be dramatic. Some pulsars have never been observed to glitch. Others glitch constantly, dozens of times over years of monitoring. The phenomenon is real widespread, and until recently deeply puzzling. Why would a pulsar which is steadily losing energy and slowing down suddenly spin faster? Where does the extra angular momentum come from? The answer, scientists believe, lies beneath the surface in the strange and exotic layers inside a neutron star. Remember, a neutron star is not a uniform ball of neutrons. It has structure. The outermost layer is a solid crust made of atomic nuclei and electrons crushed into a crystalline lattice. Beneath that is a layer where nuclei are so neutron-rich and densely packed that they merge into bizarre shapes, the nuclear pasta we mentioned earlier. Deeper still, the nuclei dissolve entirely, and you have a sea of neutrons, some moving freely, some locked into a superfluid state. A superfluid is a quantum state of matter, where a liquid flows without any viscosity, without friction. If you stirred a cup of superfluid helium and then stopped stirring, the liquid would continue swirling forever, never slowing down. It's one of the strangest states of matter we know of, and it exists inside neutron stars, where densities and temperatures create conditions unlike anything else in the universe. In the interior of a neutron star, a significant portion of the neutrons are thought to exist in this superfluid state, rotating independently of the solid crust above them. Here's where glitches come in. The crust of the neutron star, being solid, rotates with the overall spin of the star and gradually slows down as the pulsar radiates energy. But the superfluid interior, being frictionless, doesn't couple strongly to the crust. It keeps spinning at nearly the same rate it always has, slowly accumulating angular momentum relative to the slowing crust. Over time, the difference in rotation speed between the crust and the superfluid interior grows. Eventually, something gives. The crust suddenly cracks, or the superfluid and crust suddenly couple more, strongly transferring angular momentum from the fast-spinning interior to the slower crust. The crust speeds up. We observe a glitch. Think of it like tectonic plates on Earth. Stress builds up slowly over years as plates push against each other. Then suddenly the stress is released in an earthquake. The ground moves abruptly, Energy is released, and the system resets only to begin building stress again. Neutron star glitches are similar. They're star quakes, sudden shifts in the structure of the crust, caused by the mismatch between the rotating crust and the independently spinning, superfluid interior. The analogy isn't perfect, but it captures the essence. Slow buildup, sudden release, gradual return to equilibrium. The Vela pulsar is one of the most studied glitching pulsars, partly because it glitches relatively often, and partly because it's nearby only about 1,000 light-years away, which makes detailed observations easier. The glitch observed in 1988 was one of several. There was another major glitch in 1969, shortly after Vela was discovered, and another in 2016. Each time the pulsar's rotation rate jumped by a tiny fraction, then gradually relaxed back toward the long-term slowdown trend over weeks or months. By studying the shape of that relaxation, how quickly the pulsar returns to its normal behavior, astronomers can infer things about the interior structure of the neutron star, about how much of the interior is superfluid, about how strongly the superfluid couples to the crust. It's remarkable when you think about it that we can learn anything at all about the interior of an object 1,000 light-years away, made of matter in states we can't reproduce in laboratories, by simply watching how its rotation rate changes over time. But that's what pulsar timing allows. The precision is the key. Without the ability to measure pulse arrival, times down to microseconds, glitches would be invisible, lost in the noise of measurement uncertainty. But with that precision, even tiny hiccups in the rotation become detectable, and each hiccup is a clue about the physics happening deep inside. Not all glitches are the same. Some are large, changing the rotation rate by tens of parts per million. Others are small, barely detectable. Some relax quickly with the pulsar returning to its pre-glitch slowdown rate within days. Others relax slowly, taking months or even years. Some glitches seem to have aftershocks, smaller secondary jumps in rotation rate following the main event. Each glitch is different, and each one adds to our understanding of neutron star interiors, helping to refine models of superfluid dynamics, crust composition, and the coupling between layers. There's a pulsar called PSRJ 0537-6910, located in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way. It's one of the most frequently glitching pulsars known, experiencing multiple glitches per year. Astronomers monitoring it have detected dozens of glitches over the past few decades, more than almost any other pulsar. Why this particular pulsar glitches so often is still a subject of research, but it likely has to do with its youth and the amount of superfluid still present in its interior. Young pulsars, which are still hot and energetic, seem to glitch more frequently than older, cooler pulsars. As neutron stars age and cool, the superfluid component may change, or the crust may settle into a more stable configuration, reducing the frequency of glitches. But we're still piecing together the details. Here's something that might surprise you. Despite their glitches, pulsars are still the most stable clocks we have for certain applications. Even accounting for glitches which can be identified and corrected for in the data, pulsars remain extraordinarily regular over long time scales. This has led to a fascinating idea. What if we could use an array of pulsars spread across the sky as a galaxy-spanning gravitational wave detector? This concept, called a pulsar timing array, relies on the fact that gravitational waves passing through our region of space would very slightly change the distances between us and distant pulsars, altering the arrival times of pulses in predictable ways. By monitoring many pulsars simultaneously and looking for correlated changes in their pulse arrival times, astronomers could detect gravitational waves at much lower frequencies than ground-based detectors like LIGO can observe. And this isn't just theoretical. Multiple pulsar timing array projects are currently underway, including the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array in Australia. These projects monitor dozens of millisecond pulsars, the most stable ones, with extraordinary precision, looking for the telltale signature of gravitational waves passing through the galaxy. In June 2023, these collaborations announced evidence for a background hum of gravitational waves likely produced by countless pairs of supermassive black holes orbiting each other in distant galaxies. The evidence came from pulsars from the tiny correlated deviations in pulse arrival times across multiple pulsars scattered across the sky, dead stars serving as instruments to detect ripples in space-time itself. There's a beautiful irony here. Pulsars slow down because they're radiating energy because they're not perfectly isolated systems. And yet, that very predictability, even with glitches, makes them useful for detecting phenomena that nothing else can see. They're dying, yes, winding down towards silence. But before they fade, they're helping us understand the universe in ways we never could have imagined. When Jocelyn Bell first noticed that strange repeating signal in 1967, timing pulsars also helps us understand the interstellar medium, the thin gas and plasma that fills the space between stars. As pulses of radio waves travel from a pulsar to Earth, they pass through this medium, and the electrons in that medium affect the signal. Lower frequency radio waves are delayed slightly more than higher frequency waves, an effect called dispersion. By measuring this dispersion, astronomers can calculate how much ionized gas lies between us and the pulsar, which helps map out the structure of the galaxy. Pulsars become probes not just of their own physics, but of the space they're traveling through, of the galaxy itself. And then there's the fact that pulsars move. They're not stationary. When a star goes supernova, the explosion is often asymmetric, and the newborn neutron star can be kicked in one direction, receiving a velocity that can reach hundreds of kilometers per second. Some pulsars are moving so fast that they're escaping the galaxy entirely, flung out by their birth into intergalactic space. By measuring the proper motion of pulsars, how they move across the sky over years, and combining that with distance measurements from dispersion, and parallax astronomers can trace back where these objects came from, linking pulsars to specific supernova remnants, reconstructing the history of stellar explosions in our region of the galaxy. Every measurement refines the picture. Every glitch adds detail. Every perfectly timed pulse arriving when expected after traveling for thousands of years across the void confirms that the universe, despite its chaos, still follows rules, still has patterns, still offers handholds for understanding. But while most pulsars are extraordinary for their stability, there exists a class of neutron stars so extreme, so violent, that they make ordinary pulsars look tame. Their magnetic fields are thousands of times stronger, their outbursts thousands of times more energetic. They don't just pulse. Sometimes they explode, releasing in a fraction of a second more energy than the sun emits in centuries. On December the 27th, 2004, satellites across the solar system detected something extraordinary. A wave of gamma rays and X-rays swept past Earth so intense it partially ionized our upper atmosphere from 50,000 light-years away. The burst lasted only a tenth of a second. But in that brief moment, it released more energy than the sun produces in 150,000 years. Spacecraft designed to study distant black holes and supernova were temporarily blinded. Radio telescopes detected disturbances in Earth's ionosphere. For a fraction of a second, a single object in a distant corner of our galaxy became the brightest source of radiation in the sky, outshining everything except the sun itself. The source was SGR 1806-20, A Magnidar, a neutron star with a magnetic field so powerful it defies imagination. Magnetars are the most magnetic objects known to exist in the universe. Where an ordinary pulsar might have a magnetic field around 1 trillion times stronger than Earth's, a magnetar's field is 1,000 times stronger still. We're talking about field strengths of 10 to the 15th Gauss, sometimes higher. To put that in perspective, the strongest sustained magnetic field ever created by humans in a laboratory at the National High Magnetic Field Laboratory in Florida reached about 45 Tesla, or 450,000 Gauss. A magnetor's magnetic field at a quadrillion Gauss is roughly 20 billion times stronger than that. It's not just strong, it's strong enough to warp the quantum vacuum itself, strong enough that empty space near a magnetar behaves differently than empty space anywhere else. If you could somehow stand 1,000 kilometers away from a magnetar, which you absolutely could not survive, the magnetic field would begin to interfere with the electromagnetic forces that hold atoms together. Your molecular bonds would distort. The atoms in your body would elongate, stretched into cigar shapes by the field. At closer distances, chemistry would simply stop working. The field would be so overwhelming that electrons wouldn't orbit nuclei in the familiar way. Matter itself would restructure. You wouldn't die. You would cease to be chemistry and become something else, a configuration of particles we have no words for because it doesn't exist anywhere in our experience. The magnetic field of a magnetar is so intense that it affects space-time. According to general relativity, strong magnetic fields contribute to the stress-energy tensor, the mathematical object that describes how matter and energy curve space-time. Near a magnetar, the magnetic field is energetic enough that it has gravitational effects. The field itself, not the matter generating it, but the field bends space-time. Light passing near a magnetar doesn't just bend because of the star's mass. It bends because of the magnetic field. This is physics at the very edge of what we understand. Conditions so extreme. They bridge quantum mechanics, electromagnetism, and gravity in ways we're still trying to model. How does a neutron star develop such an absurdly strong magnetic field? The answer seems to lie in the details of how the neutron star forms. Remember, when a massive star collapses, its magnetic field gets compressed. A typical neutron star born from a star with a normal magnetic field ends up with a trillion Gauss field. But if the progenitor star had an unusually strong magnetic field to begin with, or if the dynamo processes during collapse amplified the field more than usual, the result can be a magnetor. Some models suggest that magnetars might form from very massive, rapidly rotating stars, where differential rotation in the newborn neutron star, where different layers rotate at slightly different speeds, drives a dynamo effect that amplifies the magnetic field to extraordinary levels within seconds of formation. It's a runaway process, magnetic field generating currents, generating more magnetic field, until something reaches an equilibrium at field strengths that beggar belief. But magnetors don't stay quiet. Unlike ordinary pulsars, which radiate steadily and predictably, magnetars are volatile. Their magnetic fields are so strong that they stress the crust of the neutron star itself. Imagine the crust, a solid crystalline lattice of atomic nuclei being pulled and twisted by magnetic forces a billion times stronger than anything on Earth. The crust cracks. When it does, the magnetic field lines snap and reconnect, a process similar to what causes solar flares on the sun, but at energies millions of times greater. These events are called star quakes, and they release staggering amounts of energy in the form of X-rays and gamma rays. The burst on December 27, 2004, was what astronomers call a giant flare, the most energetic type of magnetar outburst. Only a handful have ever been observed. The one from SGR 180-6-2 is the most powerful detected so far. In the first tenth of a second, the initial spike of energy was so intense that if the magnetar had been just 10 light-years away instead of 50,000, it would have caused a mass extinction on Earth. The gamma rays would have stripped away a significant portion of our ozone layer, exposing the surface to lethal levels of ultraviolet radiation from the sun. Fortunately, 50,000 light-years is far enough that we only saw the fireworks. but the fact that we saw it at all, that a single object on the far side of the galaxy could affect instruments throughout our solar system, speaks to the scale of energy involved. After the initial spike, SGR 1806-2, Zero continued to emit X-rays in a slowly fading tail that lasted for several minutes, pulsating with a period of about 7.5 seconds, the rotation period of the magnetar. The energy kept pouring out, driven by the magnetic field reconfiguring itself after the starquake. Astronomers estimated that the total energy released in the event was roughly 10 to the 46th ergs, comparable to the total energy output of the Sun over about 250,000 years, all from an object 20 kilometers across. It's difficult to comprehend that kind of power density. Not all magnetar outbursts are giant flares. Most are much smaller, though still dramatic by any reasonable standard. Magnetars in their active phases can emit bursts of X-rays and gamma rays dozens of times per day, each burst lasting a fraction of a second, each one caused by small reconfigurations of the magnetic field or small cracks in the crust. These objects are called soft gamma repeaters, or SGRs, because they repeatedly emit bursts of gamma rays that are soft, meaning lower in energy compared to the extremely high-energy gamma rays produced by other cosmic sources like gamma-ray bursts from collapsing stars. There's also a related class called anomalous X-ray pulsars, or AXPs, which emit steady X-rays at levels higher than can be explained by their rotation alone. Both SGRs and AXPs are now understood to be magnetars' different observational faces of the same underlying phenomenon. One of the most puzzling things about magnetars is how rare they are. Out of roughly 3,000 known neutron stars, only about 30 have been confirmed as magnetars. Why so few? If magnetars form from especially massive or rapidly rotating progenitor stars, those stars should be relatively common, but perhaps the conditions needed to amplify the magnetic field to magnetar levels are more specific than we think. Or perhaps magnetars are short-lived, at least in their active phase. A magnetar's intense magnetic field decays over time, not through ohmic dissipation like a regular electromagnet, because there's no resistance in a superconductor, but through more complex processes involving the crust and core. Models suggest that magnetars might only remain highly active for a few tens of thousands of years before their fields weaken and their outburst activity ceases. They would still be neutron stars with strong fields, but no longer the monsters they once were. If that's true, then at any given moment, we only see the small fraction of magnetars that happen to be young and active. There's a magnetar called SGR0418 plus 5729 that challenges our understanding. It has a relatively weak magnetic field for a magnetar only about 100 times stronger than a typical pulsar's field, and yet it exhibits magnetar-like behavior, emitting bursts, and showing the kind of activity we associate with much stronger fields. This suggests that the magnetar phenomenon might not depend solely on the surface magnetic field strength. Perhaps the internal magnetic field deep within the star is much stronger than what we measure at the surface. Or perhaps the geometry of the field matters, with complex twisted configurations being more prone to instability and outbursts than simpler dipole fields. We're still piecing it together. Another magnetar one, E1841-045, sits at the center of a supernova remnant called KES 73, the expanding debris cloud from the star that exploded to create it. This magnetar is relatively young, perhaps only a few thousand years old, and it's still embedded in the remnant, still surrounded by the gas and dust blown outward in the supernova. Observations show that the magnetar is heating the surrounding material with its X-ray emission, creating a glow that we can detect across thousands of light years. It's a vivid reminder that these objects, while extreme, are still connected to their origins, still sitting in the wreckage of the explosions that birthed them. The physics of magnetar crusts is an active area of research. The crust has to support enormous stresses from the magnetic field, forces that try to deform and break it. Scientists believe the crust of a magnetar is the strongest solid in the universe, billions of times stronger than steel. But even it has limits. When those limits are exceeded, the crust fractures. These fractures propagate at speeds approaching the speed of light, cracks racing across the surface of the neutron star, and the sudden release of stress sends shock waves through the star's interior and causes the magnetic field lines threading through the crust to snap and reconnect. The energy stored in those field lines, built up over years or decades, is released in an instant, producing the burst we observe. Think about the scale of what's happening. A crack forms in a solid crust made of atomic nuclei, packed tighter than anything in a laboratory. The crack is perhaps a few meters long, maybe less. And that tiny fracture on a star, only 20 kilometers across, releases enough energy to be detectable from 50,000 light years away. It's a reminder that size and power don't always correlate in the universe. Some of the most violent events happen on the smallest stages. Magnetars also spin, though typically much slower than ordinary pulsars. Where a young pulsar might rotate tens of times per second, most magnetars rotate only once every few seconds, some even slower. This slow rotation is thought to be a consequence of their extreme magnetic fields. During the formation of the magnetar, the intense magnetic field interacts with surrounding material, perhaps the debris from the supernova, and this interaction extracts angular momentum, slowing the newborn neutron star down much more rapidly than would happen for a pulsar with a weaker field. It's another way the magnetic field shapes the magnetar's life, not just through outbursts, but through its rotation, its interaction with the universe around it. One fascinating possibility is that magnetars might be responsible for some of the fast radio bursts, or FRBs, that astronomers have been detecting in recent years. FRBs are brief, intense pulses of radio waves from distant galaxies lasting only milliseconds, but releasing as much energy in that time as the sun emits in days. Their origins have been mysterious. But in April 2020, a magnetar in our own galaxy, SGR 1935 plus 2154, produced an X-ray burst that was accompanied by a bright radio burst. It was the first time a radio burst had been associated with a magnetar, and it suggested that at least some FRBs might come from magnetar flares in other galaxies. The connection is still being explored, but it's tantalizing. If magnetars can produce FRBs, then these strange, violent objects might be even more important to our understanding of the radio sky than we realized. There's something almost mythological about magnetars. They're the dragons of the cosmos, rare and dangerous, capable of releasing energies that would be catastrophic if they happened nearby. And yet they're real. They exist. They're out there right now, spinning slowly in the dark, their crusts stressed and cracking their magnetic fields, twisting and reconfiguring occasionally, unleashing bursts that ripple across the galaxy. They're proof that the universe has room for extremes beyond our everyday categories, for objects so strange that their existence forces us to expand our physics to accommodate them. But not all neutron stars live alone. Many exist in pairs locked in gravitational embrace with companion stars, or even other neutron stars orbiting each other in systems where gravity and magnetism, mass, and motion create dynamics unlike anything we see in our solar system. Two neutron stars orbit each other once every 2.4 hours, separated by less than twice the distance between Earth and the Moon. Each is roughly 20 kilometers across. Each contains more mass than the Sun. They circle each other at speeds approaching 1/10, the speed of light, locked in a gravitational dance, so tight, so intense that space-time itself ripples outward from their motion. Every orbit they lose a tiny amount of energy to gravitational waves, invisible ripples in the fabric of space predicted by Einstein, but undetectable by any instrument we could build. Every orbit they move fractionally closer together. In about 300 million years, they will collide, merge, and in that merger, they will create something spectacular. A kilonova, an explosion that forges gold and platinum and scatters them across the galaxy. This system is called PSRJ 0737-3039, and it's the most remarkable binary pulsar we've ever found. Binary systems are common in the universe. Most stars form with companions, two stars born from the same cloud of gas orbiting each other for millions or billions of years. When one of those stars goes supernova, if the binary survives the explosion, you're left with a neutron star orbiting a normal star. If both stars are massive enough, both can go supernova, and you end up with two neutron stars in orbit around each other. These systems are rare, but they exist, and they offer us something extraordinary. They let us test physics in ways that isolated pulsars never could. The story of binary pulsars and general relativity begins in 1974 with two astronomers, Russell Hulse and Joseph Taylor, using the Arecibo radio telescope in Puerto Rico. They were conducting a survey of pulsars when they discovered something unusual. PSRB 1913 plus 16, a pulsar, spinning about 17 times per second, had pulse arrival times that varied in a regular pattern over hours. The pulsar was moving toward us and away from us periodically, which could only mean one thing. It was in orbit around something. The orbital period was 7.75 hours. The companion was invisible at radio wavelengths, but based on the dynamics of the system, it had to be another neutron star, likely one that wasn't oriented correctly for us to see its pulsar beam, if it even still pulsed at all. This was exciting on its own. A neutron star orbiting another neutron star, both objects just a few kilometers across, separated by only a few million kilometers, moving at hundreds of kilometers per second. But what made the system extraordinary was what Hulse and Taylor realized they could measure. According to Einstein's theory of general relativity, two massive objects orbiting each other should emit gravitational waves, ripples in space-time, that carry energy away from the system. As the system loses energy, the orbit should decay. The two objects should gradually spiral inward, orbiting faster and faster as they get closer. Einstein's equations predicted exactly how fast this should happen, but the effect was so tiny, so gradual that no one had figured out how to detect it until pulsars came along. Pulsars are clocks. If a pulsar is in a binary orbit, you can measure the orbital parameters with extraordinary precision just by watching how the pulse arrival times change as the pulsar moves toward and away from us. And if you monitor the system for years, you can detect whether the orbit is changing. Hulse and Taylor did exactly that. They timed PSRB 1913 plus 16 for years, measuring the pulses with microsecond precision, and they watched the orbit decay. The orbital period was decreasing by about 76 microseconds per year. That doesn't sound like much, but it was exactly within measurement uncertainty the amount predicted by general relativity if the system was losing energy to gravitational waves. The agreement between theory and observation was stunning. It was the first indirect evidence that gravitational waves were real, that Einstein had been right. And in 1993, Hulse and Taylor were awarded the Nobel Prize in Physics. The Hulse-Taylor pulsar, as it's now known, is still being monitored. The orbit has decayed by several seconds since its discovery. Over the next 300 million years or so, the two neutron stars will spiral closer and closer, orbiting faster and faster, until finally they collide. What happens in that collision is difficult to model precisely, but the general picture is clear. The two neutron stars merge, likely forming either a more massive neutron star, or if the combined mass exceeds the limit, a black hole. In the moments before and during, the merger conditions become so extreme that atomic nuclei are shattered and reassembled, creating heavy elements through a process called rapid neutron capture, or the R process. Gold, platinum, uranium, rare earth elements. All the heavy stuff that can't be made in normal stellar fusion gets forged in neutron star mergers. The merger also produces a burst of gamma rays and a kilonova, an optical and infrared glow from the radioactive decay of those newly formed heavy elements. We'll come back to kilonovae in a moment. But first, let's talk about the double pulsar PSRJ 0737-3039. Discovered in 2003, this system is even more remarkable than the Hulse-Taylor pulsar because both neutron stars are pulsars and we can detect pulses from both of them. One called PSRJ 0737-3039. A spins 44 times per second. The other, PSRJ 0737-3039, B spins much more slowly, once every 2.8 seconds. They orbit each other every 2.4 hours, and their orbit is slowly decaying just as relativity predicts. The orbital period is decreasing by about 7 microseconds per year. Because we can see pulses from both objects, we can measure the system's properties with incredible precision. The masses of the two neutron stars, the shape of the orbit, the orientation, the rate of orbital decay, all of it can be determined from timing the pulses. And the system offers more than just confirmation of gravitational wave emission. Because the two pulsars pass in front of each other, from our perspective, we can observe eclipse effects. When pulsar A passes behind pulsar B, its signal is partially blocked by the magnetosphere of pulsar B. When pulsar B passes in front, its weak signal is modulated by the strong wind and radiation from pulsar A. These eclipses give us information about the structure of the magnetospheres, about how dense the particle winds are, about details we could never measure any other way. The double pulsar is a laboratory for extreme physics, and everything we measure matches the predictions of general relativity to astonishing precision. Binary pulsars also allow us to test relativistic effects that don't exist in isolated systems. One of these is called Shapiro delay. Light, or in this case, radio pulses traveling through a gravitational field, is delayed slightly compared to light traveling through flat space-time. When pulsar A's signal passes close to pulsar B on its way to Earth, the signal is delayed by the gravitational field of pulsar B. By measuring this delay, astronomers can determine the mass of pulsar B independently, which provides yet another consistency check on the system. Everything fits. General relativity predicts the behavior of these systems to within the measurement precision, which for some parameters is better than 1 part in a million. There's something almost poetic about using dead stars to test the theory that governs gravity. Einstein developed general relativity without any knowledge of neutron stars, which weren't even theorized until the 1930s, decades after his initial work. He worked out the mathematics, the idea that mass and energy curve space-time, that gravity is geometry, based on thought experiments and observable phenomena, like the precession of Mercury's orbit. And now, a century later, we use objects that compress matter to its limits, objects born in violence and spinning in the dark to confirm that his theory holds even in the most extreme conditions. The elegance of the universe revealing itself through the precision of pulsars feels almost intentional, though of course it's not. It's just physics playing out on cosmic scales, indifferent to our wonder. Binary pulsars also experience something called orbital precession. In Newtonian gravity, if two objects orbit each other, the orbit is a perfect unchanging ellipse. But in general relativity, the orbit itself rotates slowly. The long axis of the ellipse precesses tracing out a shape like a rosette over time. For the double pulsar, the rate of precession is about 17 degrees per year, an enormous effect by astronomical standards. We can measure this precession by watching how the eclipse times shift over years. And again, the measured value matches the relativistic prediction almost perfectly. On August 17, 2017, gravitational wave detectors LIGO and Virgo detected a signal unlike anything they had seen before. It lasted much longer than the black hole mergers they had been detecting, a chirp that rose in frequency over about 100 seconds before cutting off abruptly. Within seconds, gamma-ray satellites detected a short gamma-ray burst from the same region of sky. Within hours, telescopes around the world were pointed at a galaxy called NGC 4993, about 130 million light-years away. And they found a new bright source, a kilonova, glowing in optical and infrared light. This was the first neutron star merger ever directly observed, and it confirmed decades of theoretical predictions. The gravitational waves told us about the masses of the merging objects, about 1.1 and 1.6 solar masses consistent with neutron stars. The gamma-ray burst told us that the merger produced a relativistic jet. The kilonova told us that heavy elements were being synthesized and ejected. It was a complete picture, assembled from multiple types of light and from gravitational waves of one of the most violent events in the universe. Analysis of the kilonova's spectrum revealed the signatures of heavy elements, particularly lanthanides, created in the merger. The estimates suggest that a single neutron star merger can produce several Earth masses of gold and platinum, along with other rare elements. All the gold in Earth's crust, all the gold in your jewelry or electronics, was likely created in neutron star mergers billions of years ago, long before our solar system formed. When ancient stars collided and scattered their contents across the galaxy, they seeded the clouds of gas that would eventually collapse to form the sun and planets. We are quite literally made of stardust, but some of that stardust comes from the most extreme collisions the universe produces. Binary pulsars are ultimately doomed. They can orbit for hundreds of millions or billions of years, slowly losing energy, slowly spiraling inward. But the end is inevitable. Gravity wins. The orbit decays until the two objects touch, and when they do, the merger is catastrophic. For a brief moment, perhaps, a fraction of a second, the combined object might be a hypermassive neutron star, held up by rotation and pressure, but unstable. If the total mass exceeds the maximum mass, a neutron star can support about 2 to 3 solar masses. Depending on the equation of state, the object collapses into a black hole. The horizon forms. Space-time closes off. What was 2 spinning neutron stars becomes a single spinning black hole, surrounded by a disk of hot, glowing debris. And perhaps for a few seconds, a jet of particles and radiation, screaming outward at nearly the speed of light. The double pulsar, PSRJ 0737-3039, will merge in about 85 million years. The Hulse-Taylor pulsar will merge in about 300 million years. These timescales are long by human standards, but short by cosmic ones. Long after our sun has swelled into a red giant and consumed the inner planets, these binary pulsars will still be orbiting, still spiraling inward, still losing energy to gravitational waves we might never directly detect. But the physics is clear, the decay is measured, the fate is certain. There's something tragic in that certainty, perhaps, but also something beautiful. These systems are winding down, not through randomness or entropy in the usual sense, but through the precise, predictable mechanics of general relativity. They're clocks not just in their rotation, but in their orbits, counting down to an end that we can calculate centuries in advance. And in their dying, they create. They produce the heaviest elements, the building blocks of planets and life. Destruction and creation intertwined in the most literal way. From these colliding stars, we turn now to an unexpected use humanity has found for pulsars. Because their pulses are so regular, so precise, and so unique, pulsars have become cosmic reference points, markers in space that could guide travelers or at least help us explain where we are to anyone who might find the messages we've sent into the void. In 1972, humanity attached a small golden plaque to the side of Pioneer 10, a spacecraft destined to leave the solar system and drift through interstellar space forever. On that plaque, among drawings of human figures and diagrams of the solar system, was something curious. A starburst pattern of lines radiating from a central point, each line marked with a binary number. These lines weren't artistic decoration. They were a map, perhaps the most ambitious map ever created, designed not for us, but for someone else. Someone far away, someone we've never met and may never exist. The lines represented pulsars, 14 of them, chosen specifically because their rhythms are unique and identifiable. If anyone ever finds that plaque drifting in the dark between stars, they could use those pulsar signatures to figure out exactly where and when it came from. We use dead stars as cosmic coordinates to mark our location in space and time. The idea came from Frank Drake and Carl Sagan scientists, deeply involved in the search for extraterrestrial intelligence and in thinking about how humanity might communicate across the vast distances of space. They realized that pulsars offered something remarkable. They're identifiable, they're relatively stable, and their periods are unique. No two pulsars have exactly the same pulse period and rate of slowdown. If you measure a pulsar's period precisely enough, you can identify which pulsar it is, even if you're observing from a completely different location in the galaxy. And if you know which pulsars you're looking at, and you can measure their directions and distances, you can triangulate your position. Pulsars are natural navigation beacons, lighthouse signals strong enough to be detected across thousands of light years. The pulsar map on the Pioneer plaques, and later on, the Voyager Golden Records launched in 1977 shows 14 pulsars relative to our Sun. Each line represents the direction to a pulsar from our solar system, and the length of each line marked in binary represents the pulsar's period. The numbers are written in a unit based on the hyperfine transition of hydrogen, the most common element in the universe, specifically the wavelength of the radio emission from that transition, about 21 centimeters. This choice was deliberate. Any civilization advanced enough to find and decode the plaque would almost certainly know about hydrogen and its spectral properties. By using hydrogen as the fundamental unit, the map becomes universal, not tied to human measurements like seconds or meters, but to something inherent in physics. Here's the clever part. Pulsars slow down over time. If you know a pulsar's current period and its rate of slowdown, you can calculate what its period was at any point in the past or will be at any point in the future. This means the pulsar map doesn't just tell you where the spacecraft came from, it tells you when. An alien civilization finding the Pioneer or Voyager spacecraft millions of years from now could measure the 14 pulsars listed, see how their periods have changed, and calculate how long ago the spacecraft was launched. They could, in theory, reconstruct not just our location, but the exact era of human history we existed in. It's a time capsule as much as a map, a message that says, we were here at this place, at this moment, in this particular configuration of the cosmos. Of course, there's a catch. Pulsars don't last forever. They slow down and eventually become too faint to detect. The pulsars chosen for the map were selected because they're relatively strong and stable, but even they have limited lifespans as useful beacons. Some might fade in a few million years, others might last tens of millions. But over geological timescales, the map degrades, the signals weaken, some pulsars might become undetectable. The map has an expiration date though. It's a very long one by human standards. For a few million years, maybe 10 or 20 million, the map will work. Beyond that, the pulsars will have changed too much or faded too much for the map to be reliable. It's a message with a built-in time limit, readable only within a specific window of cosmic time. There's something poignant about that. We sent these spacecraft out as messages to the universe, as demonstrations that we existed, that we were capable of thought and exploration. But even those messages etched in gold and designed to last will eventually become unreadable. Not because the physical plaques will decay, though they might, but because the stars we used as reference points will fade. Even our attempt at immortality through interstellar messages is temporarily bound by the same processes of entropy and decay that govern everything else. But beyond philosophical musings, pulsars offer practical navigation possibilities much closer to home. In the 1970s, scientists began proposing that pulsars could be used for spacecraft navigation within our galaxy, a kind of celestial GPS. The idea is straightforward. If you have a catalog of known pulsars with precisely measured positions and periods, and you can detect X-ray pulses from those pulsars, you can determine your position by measuring the arrival times of pulses from multiple pulsars. It's triangulation, the same principle used in GPS, but using cosmic beacons instead of satellites. The challenge is detection. Most pulsars emit primarily in radio wavelengths, which would require large antennas to detect from a spacecraft, antennas too large to be practical for most missions. But some pulsars also emit X-rays, and X-rays can be detected with much smaller, more compact instruments. In 2017, NASA tested this concept with an experiment called NICER, the Neutron Star Interior Composition Explorer, mounted on the International Space Station. NICER is primarily designed to study the physics of neutron stars, measuring their masses and radii, by observing how X-rays from hotspots on their surfaces behave. But it also includes a demonstration of X-ray pulsar navigation, or XNav. The demonstration worked. NICER detected X-ray pulses from several millisecond pulsars and used the timing of those pulses to determine the position of the International Space Station to within about 5 kilometers. That might not sound impressive compared to GPS, which can pinpoint your location on Earth to within meters, but remember, this is determining position in three-dimensional space relative to the solar system, not just on a planetary surface. And it's doing so autonomously without needing to communicate with Earth or rely on any ground-based infrastructure. For deep space missions, especially those traveling beyond the range of radio communication, or to regions where signals from Earth are weak or delayed, pulsar navigation could be invaluable. Imagine a spacecraft traveling to the outer solar system, to Neptune, or beyond, where radio signals from Earth take hours to arrive. If the spacecraft needs to know its precise position for a course correction or orbital maneuver, waiting hours for a signal from mission control isn't practical. But if the spacecraft has an X-ray detector and a catalog of pulsars, it can determine its own position in real time by observing the timing of pulses. It's autonomous navigation using the natural beacons of the galaxy. Some scientists have proposed that far future missions to other star systems could use pulsar navigation to orient themselves as they travel, maintaining their sense of position, even across interstellar distances, where traditional methods fail. There's also a military and strategic interest in pulsar navigation, though it's rarely discussed openly. GPS satellites, which billions of people and countless systems depend on, are vulnerable. They can be jammed, spoofed, or destroyed. A system that relies on natural celestial sources, sources that no one can interfere with or turn off, would be inherently more robust. Pulsars can't be jammed. They can't be hacked. They're simply there, pulsing indifferent to human conflicts and technologies. An X-ray navigation system using pulsars would provide a backup, a way to navigate even if all artificial systems failed. The practicality has limits, of course. X-ray detectors sensitive enough to time pulsar pulses are still relatively heavy and power-hungry. The technique works best with millisecond pulsars, which are bright and stable, but there are only a few hundred known millisecond pulsars compared to thousands of ordinary pulsars. The catalog needs to be comprehensive and constantly updated as pulsars evolve and their periods change. And X-ray navigation only works in space where X-rays can reach detectors without being absorbed by Earth's atmosphere. You can't use pulsars to navigate on Earth's surface the way you use GPS. But for spacecraft, especially those traveling far from home, pulsars offer a resource that's always there, always broadcasting, always reliable within the limits of measurement. There's a certain symmetry to it. We discovered pulsars by accident, thinking briefly they might be signals from an alien civilization. Now we use them as signals ourselves, embedding them in messages to hypothetical aliens and considering them as tools for our own navigation. The universe provides not through intelligence or intent, but simply by existing, by following the laws of physics that create these spinning, pulsing beacons. And we, clever and pattern-seeking, find ways to use them. The Voyager spacecraft, carrying their golden records with pulsar maps etched on the covers, are now beyond the influence of the sun's solar wind in interstellar space, traveling at about 17 kilometers per second relative to the sun. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. It won't be close enough for any inhabitants if they exist to notice. The spacecraft will be a faint, cold object drifting silently past. But it will be there carrying its message, its pulsar map, its sounds and images of Earth. And the map will still be readable, assuming the pulsars haven't faded too much. Whoever finds it, if anyone ever does, could trace those lines back to a small yellow star in a spiral arm of the Milky Way, to a moment in time when humans existed and wondered if they were alone. Some scientists have criticized the pulsar map as overly optimistic, even naive. The chances of any spacecraft being found are vanishingly small. Space is vast. The spacecraft are tiny. Even if an alien civilization exists and has technology to detect and retrieve an interstellar object, the odds of them encountering Voyager or Pioneer are astronomical in the most literal sense. And even if they did find it, would they understand the map? Would they recognize the binary notation, the hydrogen reference, the concept of using pulsars as coordinates? Or would it just be incomprehensible markings on a strange artifact? But perhaps that misses the point. The pulsar map, the golden record, the pioneer plaque. They're not really for aliens, they're for us. They're statements of hope, of curiosity, of the desire to reach beyond our brief moment and say something lasting. We use the most stable, most universal objects we could think of, dead stars pulsing in the dark, to mark our place in the cosmos. Whether anyone ever reads that message is almost secondary. The act of creating it, of thinking in time scales of millions of years and distances of light years, says something about what it means to be human, to look up at the night sky and wonder, to build and send and hope. And now, pulsars might help us navigate, might guide our spacecrafts through the solar system and beyond, using the same signals we once encoded on gold. For strangers we'll never meet, the dead stars that mark our place in space could also chart our path through it. From beacons in the void to guides on the journey, pulsars offer light in more ways than one. But as we look forward to futures where we might navigate by pulsar light, it's worth returning to the simplest, most profound thing about them. They exist, they spin, they pulse, and eventually they fall silent. There's a pulsar somewhere in the Milky Way that will spin for another 10 billion years. We don't know which one it is. Perhaps it's a millisecond pulsar we've already cataloged, spinning hundreds of times per second in perfect rhythm. Perhaps it's one we haven't found yet, hidden behind dust, or oriented in such a way that its beam never crosses Earth. But somewhere out there, a neutron star is spinning that will outlast our sun, that will still be turning long after Earth has been consumed by the red giant phase of our dying star, long after the solar system has become unrecognizable. It will spin in silence and darkness, its pulses too faint for anyone to detect, but it will spin nonetheless. The universe has room for patience on scales we can barely imagine. Pulsars don't last forever as bright detectable objects. They slow down, gradually losing rotational energy through radiation and particle winds. A young pulsar like the crab, spinning 30 times per second, will eventually slow to once per second, then once per minute, then slower still, until its rotation is so gradual that it no longer generates enough energy to produce detectable beams. The lighthouse goes dark, not because it stops spinning, but because it spins too slowly to shine. The typical pulsar has an active lifetime, the period during which it's bright enough for us to detect, of roughly 10 to 100 million years. After that, it fades from view. It becomes what astronomers call a dead pulsar, still a neutron star, still spinning, but invisible to our instruments. But even dead pulsars persist. A neutron star once formed is stable essentially forever. Barring a collision or some other catastrophic event, it will exist as long as the universe does. It might cool over billions of years, radiating away the residual heat from its formation, until it reaches the background temperature of space just a few degrees above absolute zero. It might crystallize its crust and perhaps even its interior, solidifying into the most perfect crystal lattice imaginable, a sphere of frozen nuclear matter drifting through the void. But it won't decay. It won't evaporate. It will simply be cold and dark and silent, a monument to a star that died billions of years ago. There's something almost melancholy in that image, but also something strangely comforting. In a universe defined by impermanence, by stars burning out and galaxies colliding, and even atoms eventually decaying, if you wait long enough, neutron stars endure. They're scars left by supernova marks that say, something happened here. A star lived and died, and this is what remains. Their memories etched in the fabric of space-time, preserved not in thought or record, but in matter, pressed to its absolute limit, spinning silently in the dark. Pulsars have taught us so much. They confirm general relativity's prediction of gravitational waves decades before LIGO detected them directly. They revealed the existence of millisecond pulsars and the recycling process that creates them. They showed us magnetars objects with magnetic fields so extreme they challenge our understanding of physics. They became tools for navigation, for testing fundamental theories, for mapping the structure of the galaxy through their dispersion measures. They served as cosmic clocks, keeping time with a precision that rivals our best atomic standards. And they became almost accidentally symbols of the messages we sent into space coordinates marking our place among the stars. But beyond their scientific utility, pulsars offer us something more fundamental. They're proof that endings don't have to be complete. A star that exhausts its fuel and collapses doesn't vanish. It transforms into something stranger, something that continues to affect the universe around it in profound ways. The light doesn't truly stop. It just changes form, becomes something pulsed and rhythmic, a cosmic heartbeat that can last for millions of years. There's a kind of hope in that, perhaps a reminder that even after everything falls apart, there can still be pattern, still be order, still be something shining in the dark. Think about the journey we've taken through these past hours. We started with Jocelyn Bell, sitting alone with her charts in 1967, noticing a signal too regular to ignore. We watched stars collapse their cores, compress beyond anything we can recreate on Earth, spinning faster than seems possible, their magnetic fields warping space-time itself. We saw how some pulsars get spun back up, recycled through theft and symbiosis into millisecond spinners that keep better time than any clock we've built. We explored glitches, those sudden hiccups that reveal the superfluid interiors beneath the crust. We witnessed magnetars, the most magnetic objects in existence, releasing in seconds the energy our sun takes centuries to produce. We watch binary pulsars spiral toward merger-losing energy, to gravitational waves counting down to collisions that will forge the heaviest elements and scatter them across the galaxy. And we saw how humanity, in our brief moment of existence, has learned to use these cosmic lighthouses, encoding them in messages to hypothetical strangers and proposing them as guides for our spacecraft. Pulsars connect us to the universe in ways that few other objects can. They're simultaneously ancient and active dead, and alive, fading, and enduring. They're teaching tools and navigational aids, cosmic laboratories, and time capsules. They pulse in the dark, indifferent to whether anyone is listening, yet we've learned to listen so carefully that we can hear the whispers of space-time itself in their rhythms. Have you ever wondered what it would feel like to stand near one if you could somehow survive? To experience directly the impossible densities, the crushing gravity, the magnetic fields that bend light and warp space? We can't, of course. But through mathematics and observation, through timing pulses and measuring their deviations, we can understand them in ways that matter more than physical presence ever could. The universe will outlast pulsars. Eventually, in timescales measured in tens or hundreds of billions of years, the last stars will burn out. The last neutron stars will cool to the background temperature. The pulsars will have long since fallen silent, their rotation too slow to generate detectable beams. The galaxy will be dark, filled with stellar remnants, black holes, neutron stars, white dwarfs, all invisible, all cold. But even then, those neutron stars will still exist, still spinning just unimaginably slowly. They'll be the longest-lasting structures made of matter, as we understand it persisting long after everything else has faded. The lighthouses will outlive the light itself. But we don't live in that distant future. We live now in an era where stars still burn, where pulsars still pulse, where the universe is young and bright and full of signals for anyone willing to listen. And we've learned to listen. From the first confused detection in 1967 to the pulsar timing arrays searching for gravitational waves. Today we've gone from not knowing these objects existed to using them as fundamental tools for understanding reality. That's the story of science in a way. Noticing something strange, refusing to dismiss it, following it wherever it leads, and discovering that the universe is stranger and more beautiful than you imagined. Pulsars are still teaching us. New ones are discovered regularly as surveys become more sensitive and cover more of the sky. Each new discovery adds to our catalog, refines our understanding of neutron and star physics, offers new opportunities to test theories and explore extreme conditions. The fastest pulsar might not remain the fastest. A more extreme magnetar might flare somewhere in the galaxy. A closer binary pulsar might be found, giving us even better measurements of gravitational wave emission. The field is still active, still evolving. The dead stars, it turns out, have more stories to tell. And there's something fitting about ending a long, quiet journey through the cosmos with pulsars. They're restful in their regularity, even as they represent some of the most violent and extreme physics imaginable. They pulse in the dark like slow breaths, like a heartbeat steady and sure. They ask nothing of us. They simply exist, following the laws of physics, spinning and shining and slowly fading. But before they fade, they give us so much. Knowledge, guidance, wonder. The chance to understand just a little better what it means to live in a universe that creates such objects, that allows matter and energy and space-time to interact in ways that produce spinning stellar corpses that outlast empires and species and continents. The lighthouse keeper doesn't need to know that ships are watching. The lighthouse shines regardless its beam, sweeping through the dark regular and faithful and patient. And pulsars, the cosmic lighthouses, shine the same way. They don't shine for us. They shine because that's what physics demands of a rapidly spinning, highly magnetized neutron star. But we benefit from that light nonetheless. We navigate by it. We learn from it. We encode it in messages and hope that someday someone else might see it and understand. The pulse continues. Across the galaxy, hundreds of thousands of pulsars are spinning right now, most too faint or too distant or too misaligned for us to detect. But they're there, each one a story of collapse and transformation. Each one a clock marking cosmic time. Each one a voice in the dark saying, "I was a star once. I burned and I died. But I didn't disappear. I'm still here, still turning, still shining in my own way." And we, on our small blue world orbiting an ordinary star in an ordinary spiral arm, have learned to hear those voices and understand what they're saying. Thank you for traveling with me through this quiet exploration of pulsars, these remarkable objects that began as stars and became something else entirely. something that pulses and persists and teaches us about the universe in ways nothing else can. I hope you found wonder here in the steady rhythm of dead stars, in the mathematics of spiraling orbits, and the realization that the universe creates beacons without ever intending to simply by being itself. If these cosmic stories bring you peace, if they help you see the night sky differently, remember there are more journeys waiting, more phenomena to explore, more physics to unravel, more quiet corners of the cosmos to drift through together. Each story is a pulse in its own way, a signal sent into the dark, hoping to find someone listening. And you listened. Thank you for that. The Pulsars will keep spinning long after this moment fades, long after we're gone, long after anyone remembers that we once looked up at the sky and wondered. They'll spin in the dark, faithful to nothing but physics, beautiful in their indifference, perfect in their persistence. And perhaps that's enough. Perhaps that's all anything needs to be. Sleep well, dream gently. And when you look up at the night sky, remember that between the stars, you can see there are beacons pulsing, lighthouses spinning, dead stars still shining, still speaking, still keeping time in the endless dark. Good night.